Welcome to nuclear physics. Until now, your study of physics has largely focused on the macroscopic world of forces and motion, or the atomic world of electron shells. Now we dive into the very heart of the atom. The nucleus is unimaginably small, roughly 10 to the minus 15 meters across, yet it contains almost all the mass of the atom and the most concentrated energy in the universe. This unit sits at the intersection of fundamental forces and modern physics, bridging theoretical quantum concepts with monumental real-world applications. You will discover that mass and energy are not separate, conserved quantities, but interchangeable faces of the same coin. This concept alone unlocks our understanding of how stars shine and how nuclear reactors generate electricity.
The story of this unit moves from structure to transformation. We begin by defining the static properties of the nucleus. You will explore how the strong nuclear force overcomes immense electrostatic repulsion to bind protons and neutrons together. We will calculate the exact radius of a nucleus and use the empirical formula to prove that nuclear density is remarkably constant for all nuclides. We will also define isotopes with the exact precision Cambridge examiners demand, understanding how atoms of the exact same chemical element can have different masses and how to calculate their relative atomic mass. Once we understand what a nucleus is, we examine how it changes. You will write and balance nuclear equations for induced reactions like fission and fusion, ensuring the strict conservation of nucleon number and charge. We also cover natural radioactive decay. You will identify daughter nuclei and distinguish between the ionizing and penetrating properties of alpha, beta, and gamma radiation. Cambridge mark schemes are exceptionally rigid here, so you will learn to state precisely what it means for radioactive decay to be both random and spontaneous.
Finally, we quantify these transformations. This is where the heavy mathematical lifting of paper 4 occurs. Where does the immense energy of a nuclear reaction actually come from? It comes from missing mass. You will calculate the mass defect, the physical mass lost when nucleons bind together, and convert it into energy using Einstein's famous mass-energy equivalence principle, E equals mc squared. You must become completely fluent in converting between kilograms, atomic mass units, and mega-electron volts. A single misplaced power of 10 here will cascade through a 4-mark calculation. To explain why reactions happen at all, we use the defining graph of the unit, the curve of binding energy per nucleon. You will use this peak at iron 56 to explain the apparent paradox of how splitting heavy nuclei and fusing light nuclei both push nuclides higher up the stability curve. Any reaction that moves a nuclide higher up this curve results in a more stable nucleus and a colossal release of energy.
You are now ready to tackle nuclear physics. By the end of this unit, you will confidently calculate nuclear dimensions, balance complex reaction equations, and seamlessly convert between atomic mass units and mega-electron volts to find the energy released in any nuclear transformation. Let's begin.